Okay, so welcome everyone to the first seminar of the semester. And we have the pleasure of having Morgan Shirley here to talk about larger corner-free sets and high dimensions.
Hi everyone, thanks for having me. I'd like to tell you about this connection we were able to exploit between communication complexity and additive combinatorics. This is joint work with Leanna, who's going to be starting as a postdoc at the University of Victoria. Tony, who's at Columbia, Suhail's at Lisbon, and Adi Shraibman's at the Academic College of Tel Aviv, Yafo. Let me start out by introducing you to the K-term arithmetic progression. KAP for short is a set of K numbers such that the difference between any two consecutive numbers is the same. It's a set of the form A plus B, A plus 2B, etc. And a major open question in additive combinatorics is if we have the integers between 1 and n, how large can a subset of that range be that does not contain a K-term arithmetic progression? Let me give you a bit of history on this. So K equals 3 is the first interesting case. In 1946, Behrend gave a lower bound, that is a proof that there is a 3AP free set of this size, with density that looks like this, sort of quasi-polynomial 1 over 2 to the order square root log n. And on the upper bound side, so by upper bounds I mean at this size, certainly the set contains a 3-term arithmetic progression. There's been a long line of work since Roth in 1953 up to the recent results of Kelly and Mecca at last year's Fox, showing that Behrend's bound is sort of the right shape. We should expect that the true answer looks like this. They get, instead of 2 to the square root log n, they get 2 to the log n to some beta, where beta's been improved over the subsequent few months. I think the current state is that it's 1 over 9. So a fairly small gap, especially when compared to the result of Roth from 1953. What about for general K? In 1961, Rankin gave a generalization of Behrend's construction. In particular, at K equals 3, Rankin's construction is exactly Behrend's construction. On the other hand, upper bounds for general K are much more difficult to come by. Samaretti's theorem in 1975 famously said that if you have a set of constant density, then it must contain a K-term arithmetic progression. And the best that I'm aware of, there might be a subsequent improvement recently. I apologize if I've missed that. But the best that I know of is this Gowers paper from 2001, where we have some very small density discrepancy that we can account for in the upper bound. Okay. So the main character of this talk is going to be the corner. A corner is a set of points in a higher dimensional space. It contains a point, and then the point at the same distance away in every dimension. So this is a 2-dimensional corner here. It has a point xy, and the point c away in the x dimension, and the point c away in the y dimension. And again, we can ask the same question. If we have the integer lattice in k dimensions bounded by n on each side, how large can a subset of this be that does not contain a corner? Okay. For the first interesting case, which is k equals 2, it turns out that we can adapt Behrend's construction in a way that we'll see later in this talk to give a set of the same density that is corner free. And on the other hand, upper bounds are very hard to come by. Einstein and Samaretti showed sort of the analog of Samaretti's function, Samaretti's theorem. And the best that I know of is this result by Shredov in 2006, showing this relatively very weak upper bound. Let's unwrap what the constant is here that I've been hiding by this big O term. Turns out to be 2 times the square root of 2. Linial and Shraibman in 2021 gave the first improvement in the higher order terms of Behrend's construction by improving this 2 times square root of 2 to some value which is 2.402. This was quickly improved by Green, who has got us to the current world record of 1.822. And for general K, again, for the lower bounds, we can do the same thing. We have Rankin's construction of KAP3 sets for general K. We can turn this into a similar lower bound for corners. On the other side, we know basically nothing about upper bounds for the general K case. We know that it must be of subconstant density. I've been told that subsequent work has gotten this down to like a log star sort of thing. So there's still quite a bit of work that needs to be done here. Okay, our new result is to get an improvement on Rankin's bound in the big O term here, similar to what Linial, Shraibman, and Green did for the K equals 2 case. And as I said, these recent improvements were sort of intuitively discovered through an analysis of this problem using communication complexity. A brief introduction to communication complexity. We have 2 parties, customarily called Alice and Bob. Alice has some input X, Bob has some input Y. They exchange messages according to some protocol with the goal of outputting the value of some function on their joint input. And for this talk, I'll just be focusing on functions that have Boolean output. We say a protocol is efficient if the number of bits sent is polylogarithmic in the length of the input. We can also consider randomized communication complexity. Here we give Alice and Bob both access to some source of randomness. We let them use the randomness when computing their function. And now we allow that there's some small chance of error. We only want them to output the correct answer with high probability. So this is analogous to the P versus BPP problem in classical complexity. Unlike in classical complexity, we know that in communication, randomness can help an exponential amount. And an example that'll come up a couple of times in this talk is the equality function, where the parties just want to know if their inputs are equal. This has a maximally hard lower bound in deterministic communication, but there's an efficient randomized protocol. Okay, so let's say we now want to generalize our 2-party communication model to more than 2 parties. So we add an additional party, Charlie. Sort of the first thing that you might try to do is just give every party their own input. Maybe this is the most natural generalization. And this is called the number in hand model because we can think of each player having their number written on a card that's held in their hand, secret from every other player. Another generalization is called the number on forehead model, because now we can think of that card instead being taped to their forehead. So every other player can see their input, but they can't. And this might seem like it's not the most natural generalization, but it turns out to have a very nice application to circuit complexity, proof complexity, Turing machine complexity. matrix multiplication. In this talk, we'll see that it's tightly connected with the corners problem. So we can ask the same question as we did for the two-player case: is randomness going to give us an exponential improvement? And the answer is yes. There was this result at stock this year. I said 23, but I meant 24. That shows a separation for 3 players. There's a 3-player part function that is easy randomized, hard deterministically. So what about for more than 3 players? Beam, David, Potassium, Wolfel in 2010 showed that for this certain class of graph functions, even up to some n to the epsilon number of players, there is a maximal separation. But this is by a counting argument. It only says that there exists such a function. It doesn't tell us what that function is. And I guess I'll show details after the break. So a candidate function that could be a specific function for more than 3 players showing a separation is called exactly n. In the exactly n function, we interpret our inputs as numbers between 0 and n. And exactly n evaluates to 1 if and only if the numbers sum to n. And exactly n has an easy randomized protocol. So let's look at it in the 3-player case. Alice can't see her own input x, but she can see the inputs y and z that Bob and Charlie have on their foreheads. So she can compute a guess for x. This guess is what her value would have to be in order for the function to output true. She can then use the efficient randomized 2-player equality protocol with either of the other players, Alice or Bob, who know the actual value of x, to see if x is actually equal to x prime. And the conjecture is that exactly n is hard to do deterministically. But such a thing has been elusive to prove, and in fact, there are surprising protocols for this exactly n function that do better than we would expect naively. So a maximally hard function would take order log n bits, just someone announces their input. And exactly n can be done with less. So this is a protocol due to Changerford and Lipton, actually in the paper where they introduced the number on forehead model. As with the randomized protocol, Alice can make a guess for her value, which is the correct guess if and only if exactly n evaluates to 1. Bob and Charlie can do the same thing. So now we have these 3 values, x prime, y prime, and z prime. And I'm going to let delta be the amount off we are from exactly n being true. So the value n minus the sum of our inputs. And note that every player's guess is off by exactly delta. So here's the trick. We define this value t, which is x plus 2y plus 3z. Alice can't compute t, but she can compute a guess for t, using her guess for x. And note that this is exactly t minus delta. Similarly, Bob and Charlie can compute their guesses, getting t minus 2 delta and t minus 3 delta. And these values are a 3-term arithmetic progression. They're a 3-term arithmetic progression that is trivial, that is a singleton, if and only if delta is equal to 0. And that happens exactly when exactly n evaluates to 1. Okay, so what we've done here is we've started with this number on forehead problem for exactly n, and we've reduced it to this number in hand problem where we want to know, are the values equal given the promise that they're a k-term arithmetic progression? Okay. We're going to exploit some equivalences here. If you'd like to see the proofs of these equivalences, stick around after the break. So on one hand, we have these subset problems, corner-free subsets, K and P-free subsets. The K and P-free subset problem is equivalent to the deterministic communication complexity in the number in hand model of this equality with a promise problem. And the corner-free subset problem is equivalent to the complexity of a number on forehead exactly n problem. Now, what do I mean by equivalent? I mean that if we have a larger subset in the additive combinatorics model, we have a more efficient protocol in the communication, and vice versa. And I just wanted to mention that going one direction is a fairly easy argument, but going the other direction requires a probabilistic argument. Okay? So what does this picture allow us to do? Well, Chandler, First, and Lipton showed a reduction here. So now what we're able to do is, well, we can start with a k-term arithmetic progression-free subset, use this connection to turn it into a protocol for number in hand equality. Using the reduction, this gives us a protocol for exactly n, which then gives us a corner-free set. Now that seems pretty good, except for the fact that almost a decade earlier, Aitai and Simoretti showed how to do it directly. So what are we really gaining here? And the answer is that the communication viewpoint leads us to new intuition. All of these improvements, the Linial, Shraibman, the Green, and ours, could have been done without going through the communication perspective, but framing it in terms of communication really helps reveal where the optimizations lie. So to explain where the optimizations are, first let's look at Behrend's construction. So recall that Behrend said in 1946 that we have a three-term arithmetic progression-free subset of this density. Following previous work on the problem by Salem and Spencer, we're going to map our numbers to vectors in some vector space n to the d, simply by taking the base n representation of that number. So here's an example I wrote here of 184. If our base is 10, the vector is just the base 10 representation. Similar if we have a different base. So Behrend's idea is to look at the lengths of the Salem and Spencer vectors. So we have, let's say we start out with a three-term arithmetic progression. When we map them to vectors, what we'd hope is that those vectors are in a line. And that would really help us, because it means that these vectors can't all have the same length. This is by the simple property that any 3 points, any line can only intersect with a sphere at most twice. So in particular, if we have 3 points in the line, 2 of them can be on the sphere, but the third one won't be. Okay. So if we have the 3 vectors are the same length, they can't be a three-term arithmetic progression, and so we'll color the numbers in n by the length of the vectors. I'm going to do the squared lengths of the vectors just so everything turns out to be an integer, and then we can just take the largest color, and we have our large arithmetic progression preset. The problem here is that my wish that if x, y, and z are in arithmetic progression, that their vectors are is not true. Can anyone see why? So here's an example. I have 9, 12, and 15. These are an arithmetic progression. But if I map them base 10, then there's wraparound. And these three vectors are no longer in a line. So our intuition doesn't really work here. Behrend's solution here is to simply restrict to vectors with L infinity norm less than n over 2. Then this wraparound behavior won't happen. And again, like I said, we can use a pigeonhole argument to find a length that has many vectors in it, many vectors with restricted L infinity norm, and that gives us our large 3AB free set. Great. So combining Behrend with this argument of Chandra-First and Lipton gives us an existential protocol for exactly n. What do I mean by it's an existential protocol? Well, there's two places where I don't actually know what the details are in this protocol. The first is, I mentioned before, there's this probabilistic argument where that we need to use to get a protocol from a set. Perhaps a more difficult thing to get around is that there's this pigeonhole argument in Behrend's construction. So the question is, can we get an explicit protocol? And by explicit, I mean, can I get a protocol where I can write down all the details and analyze them? Okay. Let's start out in the place that Chandra-First and Lipton left us, where we have these locally computed values tx, ty, and tz. We could take the vector representation of them. But what if these vectors have large L infinity? In Behrend's case, because he was just looking for a large set, he was okay with just throwing out the vectors that have large L infinity. But since we want a protocol that works on every possible input, we have to sort of deal with these things directly. And the idea of Linial, and Shraibman in 2019 was to explicitly reason about the possibility of carries, the possibility of wraparounds in this vector representation. So let's see exactly what they do. So remember that I'm going to rewrite exactly n to be, we're trying to compare x plus y with n minus z. Okay? Charlie, who holds z, can look at the vector representations of x and y, compute their sum through school book addition, and figure out where the carries are required in the sum. So for this addition here, these would be the carries. Charlie then communicates that carry vector to Alice. And Alice imagines Bob's input y as being modified by the carry vector using the following somewhat complicated looking formula. But the idea here is that we're going to try to move the carry into the inputs themselves by subtracting out the carry. Now, instead of being numbers between 0 and n, they're between minus n and n, but that's sort of okay. That just increases the complexity by a constant. So now you can verify that for this new value of y, the sum is going to be the same. X plus this new y is the same as x plus y. When we're doing the addition just on individual places. Okay, so how much communication does this take? So we need to send the carry vector. Charlie needs to send the carry vector, and that takes d bits. D is the number of dimensions. And then we send the lengths of our vector, squared lengths. This is log n bits. And then Alice and Bob just need to confirm that, that their vectors have the same length. This just takes 2 bits. So we can balance the complexity of this protocol by setting d to be equal to order squared log n. And this gives us an expression that matches Behrend's construction. So how do we improve this? Linial and Shraibman in 2021 observed that some carry vectors are more likely than others. Specifically, the entropy of the carry vector is less than d bits. So here's what they do. We just assume that the most likely carry vector is correct. And so we no longer need to communicate the carry vector, but we need to go back and fix the inputs where this doesn't work. We do this just by our probabilistic set translation argument, where we pick a random translation, and we pick a random set of translations of our inputs, and with positive probability over the random choice, one of these translations will get us to an input where the most likely carry vector is correct. And so we just need to communicate about that translation. And the important thing here is that the communication required to communicate this probabilistic set translation thing is the entropy of the carry vector, which I just told you is less than d bits. So this gives an improved protocol for exactly n, and therefore also the best improvement on corner-free coloring since Behrend. I said soon after Green gave a further improvement, and one could describe Green's construction. He doesn't describe it this way, but one could describe Green's construction as explicitly reasoning out what the most likely carry vector is. And this eliminates a lot of the need for this entropy analysis. Okay, what about when k is greater than 3? As I mentioned before, Rankin gives a better construction. I'll show details after the break, but in a nutshell, what Rankin does is the following. We just repeat the process of converting a number into a vector, taking the length of the vector, and then taking that length to be your new number. We repeat this over and over again with the base that we're taking in our vector transformation, shrinking every round. And if we complete the analysis, this will prove to be much more efficient. The problem is that this previous explicit construction, these previous explicit protocols can't use Rankin's construction. And here's sort of why. So Behrend is kind of this, right? We start with exactly n over numbers. We change it into exactly n over vectors. And we reduce it to equality with the AP promise. So the carry vector method of lineal potassium Shraibman, which we just saw, can sort of be seen as the way that we're converting exactly n over integers to exactly n over vectors. So let's say we wanted to follow Rankin's construction. I'll explain what this means later, but essentially Rankin is then asking us to solve an equality with a different promise. And then continue. But the problem here is that when we want to try to convert from numbers to vectors here, we're not in number and forehead setting. So the carry method that I described to you doesn't work. So the problem the carry vector method was trying to solve is that maybe we have vectors that are way up here. They have way too high values at each of their coordinates. So our first contribution is coming up with a better way of ensuring that that's the case. So what we're going to do is have Alice announce how much she needs to shift her vector by to make it small. By small, I mean small L infinity norm. And then everyone who's playing shifts their vector by this much. And notice that we didn't need much precision here in the shift. We just needed to get it into this box. And so this shouldn't take too much information or too much communication. Okay, so if other players shift their vector by the amount that Alice says, and they find that they have a vector with a long coordinate that's not within the box that we wanted, we're done. Because remember, what we were trying to do is figure out if the vectors are equal. Otherwise, we can proceed. Now the vectors are short, so the arguments of Rankin's construction work. So what is the communication cost here? We have roughly logarithmic in the number of party rounds of shifts. These shifts each take some value, our dimension value d, times some constant c sub m, which depends on what round it is. This constant is exponential. But it turns out that the fact that we're shrinking the base of our vectors outspeeds sort of the bad amounts of communication we're getting here. And if we do some very complicated arithmetic, we can show that we should choose the dimension of these vectors to be this much in each round. And this gives us a protocol whose communication complexity matches Rankin's construction. Okay, so we have this sort of vector shift technique, which is now very conceptually simple and can even be used in the number in hand setting. So that's pretty good. On the other hand, we have this carry vector technique, which was a bit technical, maybe a bit harder to explain. And was only possible in number on forehead. But the thing that Linial, Shraibman, and Green showed is maybe being in the number on forehead setting is good here, because it means that we can use the shared information that we have from number on forehead. Okay, so what we're going to want to do in order to get a similar improvement in the general K case for our protocol is to try to use the shared information in number on forehead. So let's try to do that. Again, now we're in 5 players. We're going to be trying to solve whether the sum of the first 4 is equal to n minus the 5th. I've given an example here. The first thing we might try is just to do exactly what Lineal, potassium, Shraibman do. So we have this carry vector that the 5th player can communicate to everyone. They can use it to adjust, say, x4, such that now the sum doesn't have any carries. The problem here is that the cost is too high. So I wanted the cost to be around d like it was in the 3-player case. But unfortunately, now that we're adding more than 2 numbers up, the carry vector can have numbers other than 0 and 1. And so we end up with a cost of d times log k minus 1, which is too much. Okay? What about if we try to exploit the shared information that we have? So note that the player who holds x1 can sort of make an educated guess at what the carry vector is. Specifically, they can say, okay, what if my vector is the all zeros vector? What would the carry be then? Because they can see x2, x3, and x4, they can compute what the carry vector would be in this scenario. Additionally, they can say, okay, what if I have the maximum value vector? Again, they can compute what the carry vector would be in this case. And you'll notice that between these two cases, the carry vector only differs by 1 in each coordinate. So the trick here is to have the fifth player just send the parity of the carry vector. The carry vector at each location just send whether it's even or odd. Then the player that has x1, say, can look at it and say, oh, okay, out of my 2 options for each coordinate, I know which one it is now. So I can fully reconstruct the carry vector just from these parities. And every other party can do the same. And so we can follow through and adjust x4 by the stated amount. Now this cost is just d, the number of dimensions, because we're only sending 1 bit per dimension. So this matches what we were doing in the shift technique. And it turns out that if you plug this in to our protocol, this matches Rankin's construction. Okay? Now let's try to do a lineal Shraibman and Green sort of thing. And we can observe, I'm going to let k be even because the k is odd case is a little more complicated and I don't want to get into it. If k is even, then it's most likely that the carry vector is even. So following the ideas of Linial and Shraibman, we just assume that the carry vector has all even entries, do the protocol without having to communicate the carry vector at all. And then use set translation to fix bad inputs. Okay? What's the magnitude of the improvement that we get? Well, unfortunately, it's not great. So let's let alpha be this constant here. Our result improves it to alpha times 1 minus this constant ck over log k. As k grows, this constant is approaching this function. K is this value, which looks quite ugly. And it involves this e sub k minus 1, which is the kth Euler zigzag number. So this is counting the number of alternating permutations of length k. An alternating permutation is one where we ascend and then descend and then ascend and then descend. Here are the first couple few. We actually arrived at this conclusion backwards by trying out small amounts and then plugging it into OEIS, and we get this out and we try to do the math to make it show up, and we kind of do. The idea behind the proof is that let's let n go to infinity. Then this is kind of like analyzing the probability distribution of sums of k real numbers between 0 and 1. I don't have a good intuitive explanation for why the alternating permutations should show up here. I'd be very happy if someone who's better at combinatorics could stare at it for a while and tell me. Okay, I guess I'm a little early to my conclusion, so we can go through one of the things that I was trying to do after the break, or we could just break early. Let me conclude with a summary and some open problems. So our results are that first we constructed an explicit protocol. Remember that by explicit, I mean one where we can write down all the details for the exactly n function that matches the complexity that's guaranteed by this connection to Rankin's construction of k-term arithmetic progression descent. We then analyzed the details of this protocol that we wrote down, and we found an opportunity for some improvement. So this gives us an improved exactly n protocol and an improved corner-free coloring. So open problems, First of all, our improved protocol is sort of non-explicit, it's existential. And that's because there's this probabilistic set translation argument that was. My intuition here is that the set translation thing maybe is more easy to get around than the pigeonhole thing that existed in Behrend's construction. So maybe it's possible to make our improved protocol explicit, and maybe that would reveal further opportunities for optimization. So I mentioned that we were the first improvement since Rankin of the higher order terms in the exponent of the construction. There was a reasonable amount of previous work that was attempting to improve the lower order terms of the exponent. The idea here is you can see Behrend's construction as you find a sphere that contains a lot of points. These results instead find a thin shell that contains a lot of points. And if the shell is thin enough, then it shouldn't contain any predetermined arithmetic progressions. And it seems like these ideas could just be applied to our work. We didn't do the work to do that, but I don't see any reason why it couldn't happen. And fairly recently, on the archive, there was a new paper by Zach Hunter, Lisa Sauerman, and two other authors that I'm blanking on, I apologize, that gets better three-term arithmetic progression-free sets using ideas similar to Behrend, but a much more involved argument. So it seems like we should be able to use this to construct new, larger corner-free sets, but unfortunately, existing techniques don't work here. And Green's corner-free set construction actually is still better than just if you apply the naive reduction for this thing. So it seems like new ideas are needed here to get more. Okay, thank you.
Any question?
There was a point where you used the parity argument to talk about the carry loops. Can you just repeat that?
Yeah, sure. So here, if the input x1 is low, the carry vector will be this amount. If the input's high, the carry vector will be this amount. And the thing to note here is that these are sort of off by one. I'm lying to you a little here because I didn't take into consideration what if the carry like what if we're close enough to the boundary that the carry from the previous column does something, but it turns out that if you just if you have the player that knows x1 computed from left to right, this like what I said doesn't end up being a big issue, right? And so since the carry like the morally the each carry vector entry can take one of two values. Just stating what the parity of the carry vector is sufficient for each player to reconstruct the carry vector.
And then I just had a question. Your improvement here was this improvement on the constant.
Mm-hmm.
So this is because we believe that this is the right expression, and that the only thing that can be improved is the constant there.
Is that the general belief, or?
I think for the k equals 3 case, or I guess, yeah. Yeah, I think people believe that for 3-term arithmetic progressions, we have the right shape. It's just a question of constants.
Okay.
Like I think yeah, people believe that this in this Kelly-Mecca bound where you get a log n to the 1/9, this 1/9 is just like an artifact of the proof. Actually, Raghu said at the summer school last week in Switzerland that he thought that using already known techniques, someone could probably put in a year of work and get it down to like 1/6 or something. But getting it to 1/2, it's not clear how to do that, but it seems like that should be the correct bound. For corners, I think the community is more split. The corners seem like a really easy shape to avoid. If you just like try to hand construct a set, it seems like you can do really well and while still avoiding corners. So it's unclear if it actually does follow the same shape as these 3-term arithmetic progression bounds, or if actually there's some trick that we haven't come up with yet.
Okay, interesting. All right. Well, thanks a lot. Thank you.
Okay. I had 3 parts which I deferred to after the break, so here they are. The first was about randomized number on forehead. I said that there was this counting argument that showed that these so-called graph functions, many of them were hard. So a graph function is one where if we're given the first k-1 inputs, then there's at most one value for the final input such that the function will evaluate to 1. So exactly n is a graph function, and that's the sort of one of the big reasons that people want to analyze it. And any graph function will have an efficient randomized protocol of the form that I described for exactly n. You just have the kth player compute the value g of x1 through xk-1. That is the value that would be the only value that makes the function evaluate to true, and then they just do an equality protocol to check if that's the case. And this example of Kelly-Mecca is not a graph function. In fact, it's very far from being a graph function. One of the properties that they use is that on any if you write it as a retensor, any row or column or the other thing has many ones in it.
What is the intuition behind the name?
Yeah.
Every time I ask Tony, she's like, "Oh, you should remember this. This is so easy." It's it's the function of the function graph or something. Function graph is like a thing that means something, and it maps to this this quality.
Okay.
Open problem. Come up with a better name. Okay, so let's see the lower bounds. First, I'm going to prove that there's a canonical protocol that's one way in the following sense. The player K speaks, and then every other player either chooses to accept or reject based on the message.
And they have to choose the same thing?
If they all accept, then
Then
it's an accept. If any one of them rejects, it's a reject.
Okay.
So let's assume that we have some protocol pi that may have many players sending messages. Player K computes this G value and simulates the protocol on the inputs that he can see plus this guess value locally, and then simply announces the transcript of the simulated protocol. And the other players decide whether to accept or reject by looking at the messages that they are said to have sent according to this transcript and confirming that they would have sent that message.
First, what does it mean to compute G of one of the K-1? I mean, they don't have all the inputs of G, right?
So we're in number on forward settings so they can see.
The cave player can see the.
Yeah, you can see the K-1 other things, but
Yeah.
isn't there an input missing? Or was that?
It only depends on K-1 thing.
Yeah. Yeah, so there's, this G is just the value that xk must take in order for the function to be true, given the first K-1 input. Okay, and then we just use a counting argument. There are more graph functions than there are these efficient canonical protocols. Some remarks of this argument. This also works for non-deterministic protocols. If we have the presence of a prover that sends a proof, then we can still do the same thing. And this counting argument works up to polynomially many players. So for most applications, what we want is a lower bound that works for super logarithmic players. So in some ways, this counting argument is much better than even what we are dreaming for. Okay, so the next thing that I skipped was I said that there were these equivalences here. And the probabilistic argument that I was glossing over here is this same set translation thing that we saw later on the top. We're going to use probabilistic set translation to transform these sets into colorings. So going from colorings to subsets is easy. You take the largest color, and that's a dense subset. Is everyone okay with? I say coloring here. I mean a coloring where every color is a set that's free of whatever object we're trying to avoid. Going from a subset to a coloring, we just take the subset and we apply a random set of shifts to it, and with non-zero probability, these shifts will have covered the entire domain. And so we can just color each point by we choose some ordering on our shifts, and it's the first shift that hits that point. Okay. So in general, going from colorings to protocols is going to be fairly easy. So as a warm-up, going from K-P3 colorings to number of hands promise equality protocols. You just have Alice announce the color of her input, and then Bob and Charlie announce that they agree. And since the coloring is said to be 3AP3, if they all agree on the color, then that meant they must have had the same place. So equality is true. In the other direction, you tend to have to do something a little more clever, but it's not too complicated. So we're going to start out by we're going to color each number between 0 and n with the transcript of this equality protocol when they are all equal. So on values w, w, w. So let's assume, speaking of contradiction, that we have some three-term arithmetic progression, w, w plus d, w plus 2d, that has the same color. So the protocol then has the same transcript on all of these inputs. But then notice that this protocol incorrectly accepts w, w plus d, w plus 2d because for this input, every player has one of these inputs that they can't distinguish it from. So Alice would not be able to tell the difference between this first one and this bad input, Bob the second, Charlie the third, and so they would proceed according to the same protocol and incorrectly accept this this non-equal thing. Okay. And like I said, going from corner-free colorings to exactly on protocols is fairly easy. Alice is going to look at the color of n minus y minus z and y. Bob x and n minus x minus z and Charlie xy. So what Alice has was x plus delta y. What Bob had was x, y plus delta, and Charlie has x, y. So this is a corner, and the colors are the same if and only if the delta value is 0. Okay, in the other direction, we're going to color x, y on the protocol transcript on x, y, and then the value that makes exactly untrue, n minus x minus 1. Again, let's assume, seeking a contradiction, that there's some non-trivial corner that has the same color. So what that would mean is that we have the same transcript on all three of these inputs. And again, now we can construct a new transcript on which we should have answered no, but we have the same transcript. So in particular, Charlie doesn't know what z is, so he can't tell the difference between this and this. Alice doesn't know what x is, so she can't tell the difference between this and this. And the same for Bob. So they all have an input on which that has the same transcript here, so they can't tell the difference between these two cases. Okay. Stop me if there are questions. Now I'll conclude by giving an overview of Rankin's construction. So I'm going to introduce a generalization of arithmetic progression called polynomial progressions. This is a set, actually, we're going to now allow it to be a multi-set where we have some degree m polynomial, and we're going to evaluate the polynomial on 0, 1, all the way up to k minus 1. These are the points. So the main theorem of Rankin, and I also want to shout out this this note of Wamba and Lacey. I think it gives a very intuitive explanation of what's going on here. So if we have k points, which are in a degree m polynomial progression, such that the degree is not too high, there should be more than twice as many points as the degree. The vector forms of each of the points have low L infinity norm, where now I'm going to be stricter than Behrend and say you have to be like exponentially small in the degree. And not all of the points are the same. Then if you take the lengths of the vectors, this is a degree 2m polynomial progression, and they're not all the same values. So this is a sort of higher degree analog of the there's no sphere contains more than 2 points on a line.
Can you remind us what vector f is?
So that's the base n the base n representation of that number, where n is a value I get to choose. I get to choose the base.
It's the same parameter as the second.
Yes, it is the same parameters there. Good, thank you. Okay, so yeah, as I just said, Behrend's construction can be seen as a special case of this. So is k greater than 2m? Yes. There are 3 points, and we're in a degree 1 sort of thing. So 3 is greater than 2. And Behrend also required that we have this no coordinate was too large. 2 to the 1 is just 2. And so yeah, if the lengths are all the same, then it must be that the points are all the same. If the points are in three-term arithmetic progression. So Rankin's construction is just basically we do this observation over and over again. We're starting out with a k-term arithmetic progression. Turn it into vectors, take the lengths. This is a k-term quadratic progression. Turn it into vectors, take the lengths. It's a quartic progression, on and on and on, up to like logarithms, many steps. And so now, if this thing at the end is just 1 point, then it must mean that the arithmetic progression that we started with was just 1 point. I alluded to this before. We're really restricting the sets of vectors here because we have this exponentially increasing restriction. But each time we do this, the range of possible values goes from n to the d to n squared d. So this is the range of the possible lengths of vectors in n to the d. And this shrinking of the range of values more than counteracts the increasingly strong restrictions we're putting on the vectors in our sets. Okay. That's all I had. Are there any further questions?
Maybe this is for everyone, just to clarify, in the page before, we required, well, actually the general form, we require k to be greater than 2m. Is it because of the geometric fact that when you solve the equations of degree k polynomial, degree k, that's
Yeah,
when you want to solve the intersection of the sphere, the number of solutions.
Yeah, is at most 2 times m. Yeah. So if you have a quadratic equation in a sphere, it's like a parametrically quadratic equation in a sphere, then they only intersect at most 4 times. Okay, let's get a cake and beer.
Well, thanks a lot. Thank you.